Hello, everybody. Yeah, my name's Jeremy. I'm a researcher at Alexandre Foray, and I'm going to be presenting the work we've been doing together with some of my students, Axel, who's here today in the room, and Baptiste, who's now doing a PhD at the University of Sherbrooke, on the energy consumption of superconducting cat-qubit operations. Just a quick reminder for the people who might not be aware. Alexandre Foray is a quantum computer manufacturer. We work with superconducting technology based on superconducting cat-qubits. And so this is an example of one of our 4 cat-qubit devices. And the company itself is focused on FTQC. And so unlike the 2 previous talks, which have been focused a little bit more on NISC applications, this is something that we don't work on at Alexandre Foray. So let's get into it, and let me talk to you about what the cat-qubit is. So cat-qubits live in weakly anharmonic microwave resonators, which work between 4 and 8 gigahertz, and they have high quality factors, so they're long lifetime modes. And so I've highlighted here in blue the memory mode in which we're going to store the cat-qubit. And so you'll find this electron microscope image throughout the talk, where I keep adding bits to the picture. And so we work in a 2-dimensional computational subspace embedded in this infinite Hilbert space of the microwave resonator. And the Z basis states of the encoding are given approximately by the plus and minus alpha coherent states, which are represented here by their Wigner functions. And along the x-axis of the Bloch sphere, you find the positive and negative superpositions of alpha and minus alpha, which are the cat states. And so this is why the encoding is called cat-qubits. And so cat-qubits have a really nice property, is that they have biased noise. And so you can see this along the z-axis. The plus and minus alpha states, when alpha becomes large, the amplitude of the state becomes large, they have the overlap of the 2 states goes to 0. And so here we show that this is an experimental piece of data. As a function of the number of photons in the memory, the bit flip time increases exponentially, reaching very macroscopic times of multiple seconds. Just a shout out to Alexandre Foray. We hold the record for bit flip times in superconducting circuits at the moment. And we don't pay that much for this, so there's no free lunch, but lunch is not very expensive today. And so when you scale the number of photons again here, I've traced just the phase flip rate. So this is the other type of error, the error along the x-axis. It only increases linearly with the number of photons. So cat-qubits have a noise bias. That is to say that the error times along the z-axis are around tens of seconds, along the x-axis 1 microsecond, which if you compare with other superconducting circuits, which have more like 100 microseconds along each axis, is quite different. Okay, so the question you want to ask yourself then is, what if I make the hypothesis that there are just no bit flips? And so when I mean there are no bit flips, I mean that the physical bit flip error times the number of physical qubits per logical qubit is smaller or equal to the logical phase flip error. And in this situation, my quantum error correction code only needs to correct for 1 type of error, the phase flip error. And so unlike usually in superconducting circuits, you have this surface code which is 2-dimensional, where each dimension can be seen as corresponding to correcting 1 type of error. In cat-qubits, you only need to use a 1-dimensional repetition code here, which is just a chain of cat-qubits, which corrects for the phase flip errors. And so if you combine this with the fact that these 1-dimensional codes have high error thresholds, and that the architecture is compatible with LDPC codes, we estimate that for large-scale problems, we'll need about 200 times less physical qubits than other superconducting platforms. So this is what we call our hardware-efficient approach, and it's great. But at the Quantum Energy Initiative workshop, what we're interested in is what is the energy consumption. So is it actually more energy efficient to work with cat-qubits? And how does it compare to other platforms? So I'm not going to answer these questions today because they're quite difficult, but I'll start giving you some elements of answers throughout the presentation. And so you've already followed a cat-qubit 101 course. Congratulations. You've all graduated. And so now I'm going to talk about defining the energy consumption. So I think you have to be a bit careful about how you define the energy consumption at what scales. So I'll talk about that. And then we'll look at the energy consumption of the stabilization of the noise bias of cat-qubits and of a single qubit gate. All right, so I see optimizing energy consumption as a systems engineering challenge. And you can optimize the energy at different scales in the system. And I'm going to start with defining what I call a fundamental operation. So this is just like an abstract vision of what an operation is. So you can see it as a two-level system represented by a Bloch sphere interacting with a coherent field. And if you want to make this vision become reality, you have to make some kind of choice of your chip architecture. So you have to specify the frequencies, the couplings, the layout. And at this stage, so once you've fabricated the device, you can, or given here, you can like measure or calculate the chip level power consumption. So this is the power consumption you would have if you placed a spectrum analyzer at the entrance of the chip, and this would be the reading you would get on that spectrum analyzer. But in practice, that's not actually the power you're using to operate the device, because you have the cost of classical control on top of this. You're operating it at room temperature. Superconducting circuits work in a cryostat, and so you have to take into account the fact that you have attenuators and that the cryogenics can have some kind of maximal efficiency given by the Carnot factor. And so what I call the useful power is the power which you're actually using at room temperature to operate the device. We have EDF in the room, and I'm sure they're pretty disappointed by this number. They're like, we're not going to make any money off this. And thankfully for them, it's actually not the power. It's not the amount of power we have to pay to the energy providers. This is the build power, and the reason is that the enabling hardware we use is inefficient. So there's this massive overhead between the useful power and the build power in our systems. And so at each stage, as you go through the system here, there are different things you can do to optimize the power consumption at each stage. And so the first message of my talk is that, first of all, I'm going to talk about the useful power. And the reason I'm not going to talk about the build power so much is that at Alexandre Foray, we don't have that many ways of leveraging this build power down. So it depends a lot on the enabling hardware manufacturers. And so I think for me, one of the messages I want to get across today is that we need to work on this, because this is where the power overhead is, and I think this is almost universal in all the quantum computing systems. All right, so let's talk about the energy consumption of noise bias. So for that, we have to go a little bit more in detail into how cat-qubits work. And so I said that the cat-qubit lives in the high Q mode, and in practice, it's coupled to also a low Q mode, which we call the buffer, coupled to the environment through a rate kappa b. And they're coupled together through a four-wave mixer. And so if you drive the four-wave mixer at the correct frequency, what you can do is you can engineer a 2-to-1 photon exchange between the memory mode and the buffer mode. So this gives you this kind of flip-flop Hamiltonian you can see here. And additionally to this, we add a drive mode add a drive on the buffer mode so that we don't just continually deplete the photons from the memory, but we arrive in some kind of steady state. And so if you put yourself in the adiabatic elimination regime, where the exchange between the buffer and the memory mode is slower, much slower than the rate at which the buffer mode is coupled to the environment, then from the memory mode's perspective, it looks like it's exchanging two photons with the environment. And so this is summed up by this Lindblad master equation here, and where the steady states are just the superpositions of the plus minus alpha coherent states, which are the basis states of my computational subspace. So this is, you can imagine living in this double well potential where the minimum, in this semi-classical model where the minimums are given by plus and minus alpha. Okay, so I need to implement this in my circuit. So what I've done is I've taken my SEM image and I've highlighted for you the different elements with the colors which correspond to the modes to which they belong. And I can also make a circuit model which corresponds to this diagram. And I'm going to parameterize it with different quantities which describe the physics of the individual elements. So, for example, the Josephson energies or the coupling strengths to my drive lines. And thanks to this, I can write down expressions for the power at the chip level which I'm going to need. So this is the power according to the Hamiltonian drive strength epsilon d. This is the power I would need if I put a spectrum analyzer at the entrance of the chip. And then this is the same for that conversion pump that I was talking about. So the total power you need to stabilize a cat-qubit is the sum of these two terms. And so now I have basically created a relation between something that I can measure sort of macroscopically and the circuit parameters which I can control or simulate. So there are just a few additional details I have to go through before I can talk about how we're going to, the exact values for this power. So first of all, it's the useful power we're interested in, not the chip power. And it's just, so in the MNR paper that was presented just earlier, it's shown that this is just a proportionality coefficient which depends on the attenuations and the temperatures of each stage. In practice, we also have to take into account that the memory mode doesn't have an infinite quality factor, so there is some kind of loss, which is given by kappa 1 here. And that I'm going to talk now in terms of alpha and the 2-photon loss rate, and not in terms of the Hamiltonian drive strengths, which are a little bit more difficult to get any intuition for. All right, so what I'm going to try and do is I want to optimize the power consumption for different bit flip times. And so coming back to this MNR framework, the resource I'm going to use is this useful power for the stabilization. I'm going to fix the bit flip time, so that's my metric, for which I have an analytical expression here. Under a constraint, kappa 2 bigger or equal to 100 times kappa 1. This constraint is coming sort of out of nowhere. It has to do with the way error correction works with cat-qubits. And I'm assuming that the thermal population of my modes is 0. All right, so the first thing I see is that this bound that I was given is, we hit the constraint given by quantum error correction. So the minimization really wants you to have the lowest 2-photon dissipation rate possible, essentially. And that's because the useful power which is associated with the conversion, the buffer to memory photon conversion, is quite high, 81 milliwatts with the parameters that I've used in this simulation. And if I compare this with a graph, which on the x-axis has the bit flip time, on the y-axis the useful power which corresponds to that buffer drive, I see that I do have some kind of increase. In fact, this is quadratic. But the scale of the power consumption is much smaller. I'm talking nanowatts. So one way of interpreting this graph is that once you've created a cat-qubit, having very, very long bit flip times, it just comes for free in terms of power consumption. This axis is really negligible compared to the fact that you've had to engineer this 2-photon dissipation through the switching. All right, so so right now we actually haven't done anything. We've just created a qubit which has a very large noise bias. So let's try and operate a single qubit gate. So this, I've chosen the Z gate here, which is just a rotation around the Z axis of the Bloch sphere. It's just the equivalent of the X gate in transmon qubits, but for cat qubits. So the way it works is we add an additional memory drive, an additional drive at the memory frequency here to our system, and it's going to lift the degeneracy between the plus and minus alpha states. And this is going to create a Rabi oscillation in the XY plane. And so another, maybe a little bit more hand-wavy, but I guess intuitive way of seeing it is that if you have the stabilization on, then the blobs which correspond to plus and minus alpha in the Wigner function, they stay in place. And the memory drive, perpendicular to this, is going to roll the fringes, which changes the parity of the cat state such that you're rotating around the z-axis of the Bloch sphere. Okay, so my circuit model changes a little bit. I have to add an extra port with a coupling rate gamma A. And I have to adjust the on-chip power that I want to optimize over, which is just the stabilization power, because those two drives haven't gone away, plus the power which is associated with the memory drive. So what I'm going to minimize, if I come back to MNR, I'm minimizing the useful Z-gate power. And I haven't introduced this, but there's a formula for the probability of a phase flip during a Z-gate, which is given here. And yeah, we have an analytical expression for this, which depends on the circuit parameters and on alpha and kappa 2. Under the same error correction constraint that I had previously, but now I'm just going to set the bit flip time to 100 seconds, because we saw in the previous part of the presentation that this basically came for free. And I'm again assuming the thermal population is 0. All right, so now the plots start getting complicated. We're in that part of the hockey stick of the presentation where you have to stay awake. On the x-axis, you have the memory drive strength here. And then on the y-axis, you have the ratio kappa 2 over kappa 1. It's just so that it's adimensional. It's a good way of thinking about error correction in cat-qubits. And the color scheme here, from blue to yellow, is the power consumption for each regime of parameters. And I've overlaid these gray lines, which correspond to ISO power lines of the color scheme, just so that it's easier to see. And on top of that, I have in red, in different scales of red, the probability of having a phase flip here. And so the way you would read this graph is, let's say you have a system operating at kappa 2 over kappa 1 of 400, epsilon z over 2 pi 1.25 megahertz. Then I get to here. That means that the phase flip rate of my z-gate is about 10%. And so you learn a few things from this graph. First of all, we have this black line, which corresponds to the minimum power required for each individual phase flip probability. So this is really the result of that MNR optimization. And you see that the power depends very little on the z-drive, right? These ISO power lines are parallel to the x-axis. So again, like the bit flip, the z-gate comes for free once you've got this cat-qubit stabilized. And in fact, I'm happy to take questions about this. It's for the same reasons, essentially. So one of the things that you can ask yourself is, we call it quantum energy initiative and not quantum power initiative, right? So what happens if I optimize the energy instead? And so now the metric has changed. It's just the power I had previously times the gate time. And actually, this changes the picture completely. So now the color scale is the energy. I've still got the same lines as previously, just the gray lines are now the ISO energy lines. And you'll see that the range of the graph is completely changed. So I was looking in this little black box in the previous slide, and so now I've zoomed out completely. I've gone to the top right-hand corner. And I've got this black line now, which corresponds to minimizing the energy for each gate fidelity. And so what you learn from this, first of all, is that optimizing the power and optimizing the energy are two completely different things, and they need to correspond to different engineering requirements if you're going to deploy a quantum computer, for example. And optimizing the energy means that you need to have fast gates, that's given by this axis, with strong confinement, which is given by this axis. You're in the top right-hand corner of the graph that we saw previously. All right. So to conclude, optimizing the build power should really happen at the enabling hardware level in the short term, in my opinion, and this is something that we need to work on. Cat-qubit power consumption is dominated by the stabilization, by the fact that you need to have this 2-to-1 photon conversion between the buffer and the memory mode. And optimizing power and energy in these devices is very different. And so the next steps for us are going to be to look at studying the energy consumption of a logical memory so that we can compare cat-qubits with other platforms like transmons, for example. And the values I've given here, they're values that you can measure in the lab. You know, you put a spectrum analyzer at the output of your RF source, and you can measure these numbers. So now we can have an actual comparison between the theoretical predictions and the experimental values. All right, with that, thank you very much.
Thank you. Questions?
Thanks a lot for this very pedagogical talk. One question I had about this list or separation of 3 energy scales, where somehow the last one is the build power, which vastly dominates this whole list. What's somehow the reason why one would want to minimize the useful power if, like, in the end, anyways, the build power is the dominating source?
Yeah, Yeah, you've hit the nail on the head. So I think what this number is telling you is it's sort of, and I'll probably get told off for this, but I think it's telling you a little bit, if you take this experimental approach, this is the fundamental limit of the amount of power that you can have to run these gates, given all the things which came above, right? Because I can just choose to use a different type of equipment which has some kind of better efficiency, and I should be able to bring this number down closer to this. So if optimizing this number is basically lowering that bound. Yeah. And it requires a different skill set from lowering this number.
So this is kind of like the ultimate, say, benchmark that you want to achieve with the build power.
If you're still considering the fact that you're going to put your chip at cryogenic environments and you run it with room temperature electronics. If you run it with cryoelectronics, for example, then the image changes slightly.
Yeah. Okay, cool. Thanks a lot.
No problem.
Dear German, thank you for your talk. I'm wondering, so you estimated the energy consumption of 1 qubit, but what's about the scalability when we consider like the networks of several qubits? How would you account for the correlation between the qubits and stuff like that?
Okay, so I think I understand the question. I'll answer it in 2 parts. So first of all, we can do the same study for 2-qubit gates, so that I think answers the correlation part of the question. So 2-qubit gates, the gate you need to use for cat-qubits primarily is the C0 gate, and the C0 gate can be, the energy consumption can be decomposed into a part which is due to like a Z interaction, which I showed you here, and a part which resembles a lot the stabilization actually. And what you see is that that in the C0 gate, it's really that part which is due to the stabilization which counts a lot. And we have theoretical models. In fact, we have now analytical formulas for all the physical gates in the universal gate set for cat-qubits. It's just that today it's a bit short on time to present this. So that answers one part. And then the second part is what happens if you scale up the system? Well, then it's like how many qubits can you fit into a cryostat? And how big is the problem you can encode on a certain number of physical qubits? And there, cat-qubits have an advantage, right? Because we said that we needed 200 times less physical qubits to run large-scale problems. So you can imagine that you would also, in a sense, you need 200 times less cryostat volume. And so you have an automatic reduction of the overhead in that particular case. Yeah.